Alright then. Okay. Hello, my name is Todd Foreman. This is actually a new sort of video. As the previous one, I thought I had gotten something incorrect and it was actually correct. So I'm just going to go back to what I said beforehand, which in this case is a parallel plate capacitor is made from two plates that are 12 centimeters on each side and 4.5 millimeters apart. Half of the space between these plates contains only air, but the other half is filled with plexiglass of dielectric constant 3.4. An 18-volt battery is connected to this capacitor. So we're given a length, the length of the actual capacitor, which I've already converted to 12, pretty much 12 centimeters. Distance between the two are 4.5 millimeters. And dielectric constant for the plexiglass is 3.40, and the voltage we're given is 18 volts. So we're trying to find the capacitance. As I said before, I had to restart the video here. We first need to find the area because the dielectric capacitance equation we're going to be using would normally use the full area of whatever capacitor you would have, but because we have a capacitor where half of the area is plexiglass and the other half is air, we have to both calculate the area as well as have it, which is what I have already done, as I have squared the area, squared the 12 centimeters, and then we got 144 times 10 to the fourth meters squared, because we need half of the area for each of the calculations. We just have it into 72 times -4 meters squared. So I've already also gotten the equation, or not the equation, but the value for the capacitance for the plexiglass, as noted by CP, in which you plug in the numbers, so 3.4, 8.85 times 10 to -12 for EO, and then the halved area for A, and then the distance, which is 4.5, to then get 4.81 times 10 to the -11th force. I don't actually know the name of this specific value actually. And for the capacitance of the air, we don't use any dielectric force at all, or dielectric constant, because the air is assumed to be just 1 in this case, because we're using the dielectric constant as a sort of as a not correlation, but like it's going against the air, I guess I should say. The air is sort of the constant in this case. So because of that, there is no K included in this equation, which is A-OK, because you can still find the capacitance with just the area and the distance. So in this case, we have plugged in all of those specific ones. Oh, and this is where I remember I thought I got something wrong. That is not to the -2, but to the -4th. And as such, we go ahead and hopefully that doesn't slip off there. I'm using a box of Wheaties in order to keep the phone stable, so don't have any kind of dedicated mount in order to show the paper. And then so then that needs to be 10 to the -2 again, and that is correct. So now we divide that correctly and multiply that with this to get us a 1.41. Let's see, 1.42 times 10 to the -11F. So to find the total capacitance, it is just these two added, and that is it. We just add them together. So capacitance T is just capacitance P plus capacitance A, which is equal to 4.81 times 10 to the -11th plus 1.42 times 10 to the -11th. Let me just go ahead and add those real quick on my calculator, because they have, well, I mean, I guess I could just add just those two, but you know, there's always those past little decimals you want to make sure you don't miss out on. And it'll final answer be 623 times 10 to the -11th F. And that is the total capacitance for the system. So now we got to find how much energy is stored in the capacitor. In this case, we will be moving on to the next page because I am out of page for that. And better off if I just rip that out so I can see it for the next page myself for reference, because we're gonna need it. As we're gonna be trying to find the the energy for this system. So starting on B, which specifically states, sorry, I got a little clip here to keep this from flapping about. How much energy is stored in the capacitor? So it's kind of like a, ooh boy, how much energy is in there, eh? So at this point, it's pretty much just like the here we go. Pretty much just like the dielectric. All we do is we just plug in, and it's pretty simple actually, weirdly enough. We just plug in a basic, hold up, I had it and now I can't find it. Yes. So it was, see, oh, whoops, there it is. Okay. It was, yeah. So I was looking at Q squared over 2C, not the one right next to it, which is 1/2 CV squared. And pretty much after that, you just plug in what we got in the previous one for the capacitor, because we're also given the voltage, which is 18. So U is equal to 1/2 times the previous capacitance we got, which is 6.23 times 10 to the negative 11, multiplied by the voltage, which is also squared, and that'll just get us the whole energy for the system after I get this all plugged in properly. And 0.5, and that will be 1.01 times 10 to the negative 8th. That should be VC. Yeah, that should be VC. Oh, no. Energy, my man, energy. I'm constantly looking at the dielectric constants here. We just found like a little list. Apparently a vacuum is only 1. So as such, that's pretty much it. Find energy. I see, interesting. So now that we found the energy for the capacitor as a whole, we now need to find the energy for the capacitor without the plexiglass. So how much energy is in the plexiglass? Is in the system without the plexiglass. I guess the capacitor, not really full system, without the plexiglass. All right. So in this case, it's just as easy. And in all honesty, probably the hardest part is actually A. The second part here is just essentially, instead of having the capacitance for both the plexiglass and the air, you're removing the plexiglass, and whatever wasn't there is now filled with air. As the nature of air is to fill anything that tends to not be there, except for space. So as such, we just take the capacitance we received for air, and in this case, because it is 1.42 times 10 to the negative 11th, that was 1/2 of the capacitor. So now the other half is also that. So that essentially means that the full capacitance, I guess, I don't know what you want to call this. I'm going to call it A squared, actually. The capacitance of A squared, essentially, is, it's just 1 point, well, not really A squared, 2A, I should say. Definitely don't square them. Oops. 10 to the negative 11th times 2. because that's essentially all it is. It's just you're multiplying 2, and it takes up the capacitance. So allow me to, let's see, and multiply that by 2, and that is 2.832 times 10 to the negative 11th F. So now we need to find energy, which is the same exact equation. So it's going to be 1/2 2a, v squared. So same equation, you plug everything in, and that's pretty much it. Times 10 negative 11th times the voltage of 18. That bad boy is squared. So then 18 squared, 324. Okay. And multiply by that, multiply by 0.5, and we get the final answer of 4.58. Well, not that many. Jeez, we don't need that many stinking decimals. So we're just gonna go 5.9. Yeah, 4.59 times 10 to the negative 9th joules, because this is energy, not an electric field, as I kind of assumed at first. And that is it. That is each part of this specific problem done. Both A, well, not both, but A, B, as well as C. This is Todd Foreman. My Panther ID is 623-6580. Also listed here. Let me put that down. Here we go. Also listed here, my name. I'm not really sure what else I will require. The only thing I was confused about is whether or not I needed to do it during the test, but I was a bit concerned that bringing out my phone to record myself while it's taking a test might have been a bit problematic. So after the test, I just went ahead and immediately just found the question and just started it, and realized the dielectric stuff tends to be kind of easy, sadly. Not sadly, but good, wonderful. Anyway, I'm going to stop talking. Thank you very much for watching.